Happy to have today Gadi Fibich from Tel Aviv University. Gadi is an applied mathematician. He started 27 years ago with nonlinear optics. And along the years, he started working also on auctions. And in the recent years, he works on marketing and the diffusion of new products. And we are very happy to have today Gadi, who will tell us about the asymptotic revenue equivalence in asymmetric auctions.
Thank you, Eilon, for the invitation to speak in this seminar. I had quite a lot of collaborators on this ongoing project. Nir Gavish from the Technion, Arieh Gavious from Ben-Gurion University, Aner Sela from Ben-Gurion University, and Eilon, who you all know. Let me start with a quick introduction to auctions. So, auctions, we all know auctions. Bidders can be consumers competing for artwork on eBay. But auction is a serious thing also in the modern economy. You sell wireless frequencies, treasury bonds, flowers. A lot of things are being sold through auctions. In this case, the bidders are firms. So really understanding auctions is important for economics. And the focus of this talk is on an auction where you just bid for a single indivisible object. So there are various ways to conduct an auction, how to set up the auction rules or the auction mechanism. You have the first price auction where everyone puts their bid in sealed envelopes. The higher bidders wins the object and pay his bid. You have the second price auction. You conduct it as before, but the winner pays the second highest bid. You have the all-pay auctions. Again, you conduct it as before, put the bids in sealed envelopes, so that eventually everyone pays their bids. And there are various other auction mechanisms. We consider the following setup. We have n bidders. We know the number of bidders compete for a single object. And we assume that each one of the bidders has his own private value, VI, for the object. So I see this artwork and I know how much it worth for me to have it hanging in my living room. And this value is unknown to the other bidders, and it's distributed according to some CDF function, Fi of V. And bidders' values, we assume they are independent of each other. So we will make 4 basic assumptions. First, all bidders are risk neutral. Second, we assume symmetry among the bidders. So the valuation of bidder I, VI, is distributed according to a CDF, F of V, which is the same to all bidders. So all bidders have the same distribution function for the values, F of V. For convenience, it's on the support 0, 1. It's common to all bidders and it's known to all bidders. The object is allocated to the highest bidder and the auction rule is anonymous. So these are the 4 basic assumptions we make. And we need now to define what is the bidding strategy. So bid strategy BI of VI is a function that tells bidder I, if your value is VI, what should be your bid BI that you offer. So it is some function from 0, 1 to 0, infinity. And we assume that every bidder knows the bidding strategies of all the other bidders. And therefore, if there is an auction for something which is worth to me VI, and I'm going to put a bid of BI, I don't know the values of the other bidders, but I know their distribution and I know how they would bid for each value. And therefore, I can compute my expected payoff and my expected payment, and the expectation is taking over the unknown values of all the other n-1 bidders. And the assumption is that every bidder chooses his bid so as to maximize his expected utility. And this brings us to the notion of equilibrium. So what would be an equilibrium here? It's a set of n bidding strategies, such as for any I, the bidding strategy bi maximize the expected utility of I, given that all the rest of the bidders follow their bidding strategies. And a symmetric equilibrium is a case where everyone has the same bidding strategy. And so if all the other people follow the strategy B of V, then I should also, the best thing for me is also to follow that strategy in order to maximize my expected utility. So let's start with the first price auction. The highest bidder wins the objects and pay his or her bid. And in this case, when you do the mathematics, it's easier to work with the inverse equilibrium bid function, V of B. And this V of B turns out to satisfy the ODE, which is written here. V prime of B is 1 minus n minus 1, capital F, which is the CDF of all the values. And here little f is the probability density function. It's the derivative of capital F. So this is the ODE for the inverse equilibrium bid function in first price auction. When your value is 0, you bid 0. There's no point to bid more. So the inverse satisfies that V at 0 is 0. And so we have a first order ODE. You can solve it explicitly and you get the expression that you get here. So this is the symmetric bidding strategy in first price auction. Second price auction, highest bidder wins the object and pays the second highest bid. In this case, the equilibrium bid is just to bid your true value. I'm not going to go over the proof. It's just below here. It's 3 lines. It's a standard result. But note that it doesn't involve any ODs or nothing like that. So now let's think of this from the point of view of the seller. And the assumption is that all the bidders follow the equilibrium strategies. And so the seller cares about his expected revenue, which is the sum of the expected payments of all the bidders. And from the seller point, the key question is which auction mechanism should he choose in order to maximize his expected revenue. So the first to study this problem was Vickery in 61. And in this breakthrough paper, he computed analytically the expected revenue in first price and second price auctions with a uniform distribution for the values and find that it's the same. It was the same value, the expected revenue in first and second price auction. And it took 20 years to generalize this result to a much more general setting, and this is known as the revenue equivalent theorem, probably the most important result in auction theory, which says that under assumptions 1 to 4 that we saw previously, the expected revenue of the seller is the same for all auction mechanisms. So it doesn't matter whether you choose first price, second price, all pay, whatever, you would always have the same. Yeah, I see there's a question here.
Yes, I think it was understood, but I'm not sure you told us about uniqueness of the equilibrium. So because you compute the revenue on the basis of the solutions you gave, presumably you have to have uniqueness or to be sure that there are not other equilibria that would give another payoff, no? I think everything is known, but it's just to be sure we're talking about the same thing.
Okay, thanks. So I'm assuming that there is a unique symmetric equilibrium. And in a lot of settings you can prove that it's unique, but there is a hidden assumption that there is a unique. No, so, actually, I think even that there would be a few symmetric, there would still be revenue equivalent.
Yeah, I think so. Yeah. I think you would have that, but in the way you presented things, you might ask whether there are other equilibria in. Yeah, you just compute the revenue associated to the one
with a symmetric equilibrium.
No, but symmetric, I understand. But yes. even you have to be sure that, but I think it's true under your assumptions, but to claim things as you present them, I think you have to be sure that there are no other symmetric equilibria. And I believe it's true. I don't think it's an assumption. I think you can prove it, but to make sense of the result, it seems to me that you need some form of uniqueness. With the proviso of symmetry, I agree with that. No?
I think with symmetry, that even if you have two symmetric equilibria, there would still be revenue equivalent. I suggest we move forward and not get fixed on this point.
As you like.
Okay. So the revenue equivalence theorem had these assumptions, the 1 to 4, and they are very non-realistic. We assume symmetry, but more realistically, bidders have different distribution functions. And bidders may be risk-averse and not risk-neutral. But once you try to go to more realistic models, then the analysis becomes much harder. Typically, there are no explicit solutions for the equilibrium bids. Much less is known. The revenue equivalence doesn't hold anymore. And for example, one of the key questions in the theory has been to take the two most common auction mechanisms, first price and second price, and try to say which one is more profitable for the seller when you break this assumption 1 to 4. And what we try to do is to approach these problems using tools borrowed from applied math. And I guess if I address the question from before, that one of the problems with applied mathematicians that we are less strict about definition, we are more informal. So maybe that's why you'll have to bear with me about not everything to be maybe as precisely defined as you are used to in game theory. The focus of this talk is going to be just on asymmetric players, risk-neutral, risk-averse we've done in some other studies. But so all I want in this talk is to study what happens if I replace the assumption of symmetry with the assumption of asymmetry. So the values of the bidders would be distributed according to different CDF. Each one would have its own Fi of V. They would still all be on the same common support 0, 1. And we also denote the derivative of this capital F by little f. So that's the only change we make. So for second price auction, this has no effect. The bidding strategy is still to bid your true value. But for first price auction, once you add symmetry, in a way, all hell breaks loose. Now the model for the inverse equilibrium strategies is given by this ODE for VI prime. And if you look on this ODE, it depends on all the bidding strategies, the inverse bidding strategy of the other bidders in a nonlinear way, and they're all coupled. So we have n coupled nonlinear ODEs. We have n initial conditions, VI at 0 is 0. But if you look what happens with B equals 0, at B equals 0, this term is 0 because VI at 0 is 0. And here you derive by 0. So the right-hand side is of the form 0 over 0. And so from ODE theory, we know that you don't have uniqueness once you have a unbounded right-hand side. And it turns out, however, that there is an additional boundary condition which comes from the demand of being in equilibrium, and that is that all bidders should have the same maximal bid, which we denote by B bar. So we don't know how much is this B bar, but we know that when your value is 1, everyone bids the same B bar. So this is the complete mathematical model for asymmetric first price auctions. We have a system of n coupled ODEs with two n boundary conditions, n on the right and n on the left, and the right boundary condition is free. We don't know where is B bar. So it's a highly non-standard form of ODE system, and that's why it's very little relatively is known about it. There is a proof of existence in uniqueness by Lebrun. There are very long technical proof, but understanding this system beyond existence and uniqueness is still an ongoing research problem. So what we set out to do is to try to understand this system using various tools that we have in applied math, perturbation analysis, numerical method, dynamical system, asymptotic analysis, whatever. And let me start with the beginning, with perturbation analysis. So one thing you like in applied math is to have a small or a large parameter in your problem, because once you have a small or a large parameter, there are a whole kind of techniques you can use. So we start, if asymmetry is hard, let's start with the case of a weak asymmetry. So by weak asymmetry, we mean that the CDF of the bidders are different, but not very different. So the way we put it, they are all equal to f of v plus some epsilon hi of v. So epsilon is a measure of the difference between the CDFs, and epsilon small means that we are in the case of a weak asymmetry. If you go start with the second price auction, here we have an explicit expression for the expected revenue. We can substitute in this expression just fi equal f plus epsilon hi, and expand this r second in power series of epsilon. And when you do this, you get the expression that you have here at the bottom, that r second as a function of epsilon is r at 0, the symmetric revenue when epsilon is equal to 0. And then you have this red term, which is epsilon times something. So this something tells you what is the leading order influence of asymmetry on the revenue in second price auction, and the error is order epsilon squared. You can do the same thing for asymmetric first price auction. So here is the system that we have. We substitute fi equal f plus epsilon hi, but we need also to expand the inverse equilibrium bits in powers of epsilon. So when epsilon is equal to 0, it's just V symmetric, the expression that we know from the symmetric first price auction. Then the capital VI, epsilon capital VI, so this is the leading order effect of asymmetry on the inverse bidding strategy of bidder I, and the order of this expansion is order epsilon square. So we substitute this also in this OD system. There's a lot of technical work here, and you need to keep all the order epsilon terms in order to get ODs for capital VI of B. And you need to solve them, and there are a lot of, really, it's a very technical work, but eventually you can get explicit solution for them, and you can go back and substitute them in the expression of the revenue for the first price auction. And once you are done with all this calculation and do all the debugging, you get the following result, that the revenue in an asymmetric first price auction is R at 0, the symmetric one, minus epsilon some influence of the asymmetry on the revenue, plus error, which is order epsilon square.
Gadi, can I ask a question?
Sure.
So can you go back to the previous slide? So here you say you expand the inverse equilibrium bid in epsilon, yes, and you assume that VIB has a solution as a representation as the V symmetry plus epsilon times something plus O of epsilon squared.
Yeah.
How do you know that there is such an expansion and the expansion is not in square root of epsilon or some different order of epsilon?
That's a good point. I would give the answer as an applied mathematician. As an applied mathematician, when you do an expansion, it should always be in the parameter unless there is a good reason why it should not be in the parameter. So in 98% of the cases, it should be in epsilon. It should be a square root of epsilon if there is some double root or some degeneracy in the system. So when you just begin to work, you just do it, and you see whether you get something meaningful. And so when we did this calculation, we just assumed this expansion in epsilon without proving it. Later, when Lebron proved the existence, he also proved the differentiability in epsilon. So a posteriori, this is justified. But when we did it, we didn't justify it, we just assumed it. And I can say another thing. If this was the wrong expansion, it wouldn't work. If the correct expansion is in square root of epsilon, you won't be able to do the computation. Somewhere it would hit you in the face. Okay, so that's what we got for the first price auction. And so what we saw so far is that once we introduced order epsilon error asymmetry, this led to order epsilon change in the Sela respective revenue. So our first and our second both changed by order epsilon. So we can assume that the revenue equivalence theorem would break down with an order epsilon error. But if you look on the expression in red for the effect of order epsilon effect of asymmetry on the revenues, you see that they are the same in first and second price auction. It's literally the same expression. So the difference between R first and R second is order epsilon square and not order epsilon. And it turns out actually that this is a much more general result, that for any auction mechanism that satisfies assumption 1 to 4 with asymmetry, the seller expected revenue is R0 plus epsilon R prime 0 plus order epsilon square, where both R0 and R prime R0 are independent of the auction mechanism. And here, if I go with a long question, modulo the assumption that all the bidding strategies are differentiable in epsilon. So the classical revenue equivalence theorem told us that R at 0 is independent of the auction mechanism. What we proved is that R prime is also independent of the auction mechanism. R double prime already depend on the auction mechanism. So the difference between different auction mechanisms is order epsilon square. So let's see this numerically. We took first and second price auction. We took some two bidders. This is F1, this is F2, and we vary the value of epsilon to change the level of asymmetry. Epsilon equals 0, they are both the same, so the difference is 0. And as we increase the value of epsilon, the difference between R first and R second increases, but it increases quadratically in epsilon. And so even with 40% asymmetry, which is quite a lot, the difference is quite small. And you can say, well, you did an expansion for small epsilon. Why should it work for epsilon equal 0.4, which is not a small number? So here again, I can tell you that as an applied mathematician, when you do this kind of perturbation analysis, more often than not, they are valid outside the domain where you would think that they are valid. You can stretch them further out and they would still make sense. So what this tells us is that if we are in a case with an auction and we have asymmetric bidders, but we want to replace them with symmetric bidders. So we want to consider the homogeneous case, the symmetric case, because this is what people do in 98% of auction theory. So if we replace them such that instead of having the original FI, we would have a new FI, which would be just the average of all the FIs, and we would do this approximation. So we would replace the asymmetric revenue with a symmetric revenue. So where we take for each bidder a symmetric, the mean of all the arithmetic mean of all the CDFs. So if you do this, then the error would be order epsilon square. So if people work in auction theory and assume that bidders are homogeneous, symmetric, then the error for the revenue is typically order epsilon square. And actually, this is part of a much more general problem. And think about the following problem. We have some model with some asymmetric property, which we denote by mu1 to mu(n). And we want some outcome of this model, for example, the seller's expected revenue. And the heterogeneous model is hard to analyze or to solve. But if we look on the same model, what we consider the model with the homogeneous property, so all of these are the same, there are some average of these heterogeneous properties, this is typically way, way easier to compute. So in many cases, what we end up doing is saying we cannot handle the two heterogeneous case, so we do the homogeneous case, and we hope for the best. So we hope that we didn't make the error that we made is not so large. But then the question is, how large is this error, this approximation? So let me illustrate it with an example, not from auction theory. Let's think about this queuing problem. You have a service system with k servers. You have customers that arrive randomly at some average rate of lambda. And once they arrive, they are randomly allocated to one of the available servers. And each server has a different service time, which is denoted by mu(i). So this is a classical problem in queuing theory. It's called an MNK queue with heterogeneous servers. And let's denote by f of mu1 to mu(k) the average number of customers in the system. And if you want to know this, to solve this analytically, this is a hard problem because of the asymmetry. And the reason it's hard is you have to consider a lot of different states. Here, there's no one in the system. Here, the first customer that came was randomly allocated to this server or to this server or to this server. When the second customer arrived, you can move from here to here, from here to here to here. So overall, you have here 2 to the k different states that you have to write equation for all of them. So even for moderate values of case, the system becomes intractable. But if you're on the homogeneous case, then all of these 3 states collapse into this state, just one person in the system. All of this collapse to this. So this is a much simpler problem. And this was solved by Nir many years ago. So what you would like is to approximate the heterogeneous queue with a homogeneous one. But how accurate would be this approximation? So let's assume first that the outcome that we are interested in is smooth in the parameters. And let's denote by epsilon the level of heterogeneity of these parameters. So for example, it's the maximal difference between mu(i) and the average of these mu's. So if you just do a leading order Taylor extension, you see that the error of this approximation is order epsilon. So roughly speaking, you have a 10% heterogeneity, you would get the error would be on the order of 10%. But in many cases, people observed that the error was much smaller than order epsilon. And this is because you have to see whether the outcome you are interested in is symmetric. And by symmetric, what we mean is that if your outcome, if you change the location of mu(i) and mu(j), it doesn't affect your outcome. For example, in the asymmetric auction, if I'm called bidder 2 today and bidder 8 tomorrow, it doesn't affect the seller's expected revenue. If you think about the system that we talked about, the queue system, if you tell 2 servers to switch places, so long that customers are randomly allocated to any free server, it doesn't affect the average number of customers in the system. And it turns out that if your outcome is smooth and symmetric, then the error of this approximation is order epsilon squared. And U bar can be any average that you want. And it's a 3-line proof. It's a calculus 2 proof. It's really elementary. but it's a very important result in the sense that it tells you that once you replace the heterogeneous system with the homogeneous one, so long that you have also symmetry, you have an order epsilon square error. So let's get back to this problem of replacing the heterogeneous bidders with the homogeneous one. So if you look on the seller's revenue as a function of these CDFs, this is a symmetric outcome. If you interchange Fi and Fj, it won't affect the seller's revenue. And therefore, we know by the averaging principle that the revenue, the asymmetric revenue, is the symmetric one up to order epsilon square. And for the symmetric revenue, we have an explicit expression. And for F bar, we just put the value of the average of the Fi's, which is this. And once you put this in, you get exactly the expression that we got before, but now it's a 3-line proof instead of the 5 months it took us for first price options. But you can even get more, because if you think about it, what we really used here when we applied the revenue equivalence, the averaging principle, was just differentiability and symmetry. So we don't have to assume that it's a first price auction. It can be any auction. So any anonymous action, this approximation would work. You don't even have to assume it's risk neutral bidders. So long that you have the same risk aversion for all bidders, you can still apply this. Replacing Fi with Fj doesn't affect the outcome. You don't even have to assume that you're in Nash equilibrium. Even if you decide bidding strategies differently, so long that all the bidders use the same rules for determining their bidding strategies, you can still have this Fi changing with Fj, and so you still have the symmetry. And so, assuming there is still differentiability, then you still have this revenue order epsilon revenue equivalence for this more general setting. So until now, I assumed that asymmetry is weak, and that was very helpful because we had a small parameter epsilon. But we wanted to remove this assumption, but we still need some large or small parameter. So another parameter that we can choose is the number of bidders. So now let's assume that we have a lot of bidders. So this is will be our large parameters. And we want to analyze, we start with the first price auction, and we want to solve it numerically for large A. So how do you solve this numerically for large N? Well, you cannot integrate this OD from B equals 0 because of the non-uniqueness. So the standard method was to start from B bar, and you guess some value of B bar, and you integrate backwards, and you see whether you satisfy the condition that at 0 you are 0. And you play with the value of B bar, you do some shooting until you find the correct B bar that would give you that V at 0 is 0 for all bidders. So this is backward shooting, and with 2 bidders it works fine. If you go to 3 bidders already, it's going to find up to some point, and then the solution breaks down, the numerical solution. And that was the standard method for many years, and people tried a lot of ways to improve it, but with limited success. For example, if you look with 6 bidders, it already breaks down halfway before you reach 0. And that was a problem for us because it means we cannot do numerics with a lot of bidders, which is what we wanted to do. So what we asked is, well, why is this unstable? And can you fix it? And can we somehow avoid the instability? So that was the topic of this paper. And after working on this, we ended up concluding that backward shooting is inherently stable. It's unfixable for a large number of bidders. And so we needed another numerical method. And eventually the trick was simple. we just change the independent variables from B to Vn. So now the independent variable is Vn, the value of the nth bidder, and it's between 0 and 1. So now you work on a fixed domain. And now Vi is a function of Vn and B is a function of Vn just by the chain rule. And what you end up solving here is this nonlinear boundary value problem on a fixed domain. And it's solvable. You can use Newton method, other method, and it works beautifully. Here you see the solution with 3 bidders. Here you see with 6 bidders. And you see here we put a resolution of the bid. So you indeed see that there are 6 different bidders here. And you can go up to hundreds of bidders, no problem. So now we had a good, reliable numerical solution. So we can go and try to do some analysis. So we wanted to solve the ODEs asymptotically. And this turned out to be a hard problem. We know the limiting behavior from Wilson. We know that the limit of Bi of the bid is the value as the number of bidders goes to infinity, just because the competition becomes harder. So if you want to maintain any chance of winning, you need to increase your bidding. But we wanted to go beyond this. We wanted to know what's the difference between the bid and the V. How does this scale? And this turns out to be a hard problem, and let me explain why. Look here on the numerics with 5, 10, and 20 bidders. And the solution looks well behaved. Everything looks nice. And let me zoom in here on this area near the maximal bid. And still everything looks perfectly okay. But let me now plot the derivatives. And if I plot the derivatives, you see the near B bar, the derivatives become large. And the change you see here with 20 pairs, it's a very sharp change. There is a very fast change near B bar. In applied math, we call this a boundary layer. So you have a narrow solution near the boundary where you suddenly have fast changes. And boundary layers have a long history in applied math, going back to hydrodynamics in the early 20th century. Essentially, it's a situation like we take this ODE, and with epsilon small, and you plot the solution, it looks well behaved here, but suddenly it changed very fast near the boundary. If you just put epsilon equals 0, the coefficient of the highest derivative, you get what we call the outer solution. It's this. It matches the solutions throughout most of the domain, the red one, but not here. So for here, you need a different solution, what we call the inner solution or the boundary layer solution. It doesn't depend on X, it depends on some, the boundary layer variable C, which is X over epsilon, so it changes fast. So you need to compute this solution separately, and then you need somehow to match them in order to obtain the solution. So this was a crash course on boundary layer theory. But let me show you what it means for the asymmetric first price auction. So when you do the asymptotics for this system of ODEs for first price auction, it turns out that the solution of the inverse equilibrium bid has indeed the outer solution and an inner solution. The outer solution depends on B. The leading order term is still symmetric for all bidders. The asymmetry is only in the order n squared term. If you look on the inner solution, first its magnitude is small. It's order 1 over n squared. And it depends on the inner variable C, which is the distance from the boundary, B bar minus B, but over this is our epsilon, 1 over n minus 1 squared. So there is a very narrow boundary layer near B bar, whose width is 1 over n squared. And the solution decays exponentially as you move away from the inner boundary. So this was there are many technical things here in the calculation, but the good thing is that this allows us now to compute revenues. And we want again to compare the revenue in first and second prize auction, but now for large auctions with a large number of bidders. And we want to see how it scales as a function of n. So for the second prize auction, again, we have this explicit solution. You plug in, you just expand this using Laplace method for integrals, and you get this expansion. And here we have this little fg, which is the derivative of capital Fg, where capital Fg is the geometric mean of the CDX. So now the geometric mean is the natural term to work with. And R second depends on, here you have on this expression, and it's just a power expansion in 1 over n or 1 over n minus 1. If you go to the first prize auction, you take the expression that we got from the asymptotics here, you plug it into the expression for the revenue, again apply Laplace method, and you get another expression. And if you compare these two expressions, you see that the leading order is the same, the order 1 minus n is the same, and the order 1 over n minus 1 square is the same. So the difference between the two is scaled as 1 over n cubed. So it's a very small effect. So we wanted to test it numerically, and now that we have a code that we can handle a lot of bidders, we can do this. So we compare R first and R second. Half of the bidders have one F1, the other have F2. And you see that except for a very small number, they all lie on the line whose slope is n cubed with something. So we got indeed numerically the order n cube asymptotics confirmed. That was the good news. The bad news or worrying news was that C is small. And numerically, when you get such a small number, you start worrying, maybe this number should be 0, maybe it's already machine error or whatever. While the number should not be, when you do correct asymptotics, constant should not be small. So to understand this, let's go back to the beginning of this talk, and we saw that the difference between R first and R second is order epsilon squared. So what this means is that if you have this difference, which is C over n cubed, then this C still should scale as epsilon squared. So the correct scaling for the difference between these two should be order epsilon squared over n cubed. In other words, there are two different mechanisms that act together to reduce the revenue difference: the large number of bidders and the weak asymmetry between the CDX. And to see that this is correct, at least numerically, we took half of the bidders with F1, the other half with F2. And initially, we took 3 different values of epsilon and compute the revenue difference between first and second as a function of n. And you see it here. And indeed, the revenue difference scale is 1 over n cubed. But now, instead of plotting here R first minus R second, we multiply the outcome by epsilon to the -2. And now all 3 lines coalesce to the same line. So what this means is that R first minus R second in this scale is C epsilon square over n cubed, where C is the same for all 3 lines. And indeed, once we do this, C was almost 1 or order 1. So what this shows us is that indeed the revenue difference scales as epsilon square over n cubed.
Gadi, can I interrupt you with a question?
Sure.
So this relation of epsilon squared divided by n to the n cubed, is it a theorem, or is it general you proved it, or it is only confirmed by this example or in various other examples?
Well, I have a function, okay, R first minus R second. I know that it should scale as 1 over n cubed, and I know that it should scale as epsilon squared. So that's the only way that it can satisfy both of these conditions. So assuming the conditions for the epsilon square are set either differentiability in epsilon and whatever you need, then yes, it's a theorem.
Okay, thanks.
So let's go back to one of the first example we saw. There, when I showed you R first, R second, I said, look, it scales like C epsilon square, so it confirms the order epsilon revenue equivalence that we proved at the time. But at the time, we didn't look on the constant. We didn't care about the constant being so small. But now, if you think about it with the new interpretation, and you look on this difference as C epsilon square over n cubed, and you put n equal 2, already these constants become order 1. So, of course, stretching large n to n equal 2 is a little bit of a stretch, but still it sort of explains why this constant is small. I think I'll skip the Myerson optimal mechanism. And how am I with time, Eilon?
So we are here until 5, so 10 minutes.
So I can do the Myerson. Okay, so let me do the Myerson. So Myerson came up with a mechanism, the optimal mechanism for asymmetric auctions that would guarantee to the auctioneer the maximal revenue. It's not a practical tool for asymmetric auction, but it gives us an upper bound for how much the seller can expect to get. And for that reason, it's interesting to analyze it also for large auctions in order to see how good or bad the first or second price auctions are compared to the best that the auctioneer can do. And actually, you can compute the optimal, expand the R-opt, the revenue under Myerson optimal mechanism as power series of n, and again get the same expansion as we had for first and second. So it shows that first and second are both order n cube away from Myerson optimal value. And actually, they are order epsilon square over n cube by the same argument that we had before. Now, we had this order 1 over n cube for 3 different auctions, for first, second, and Myerson. But we wanted to generalize to get a general result like we had for the order epsilon square. So to have that all auction mechanism are order 1 over n cube revenue equivalent. And we did manage to do this, but we needed 9 conditions. And these conditions are satisfied by second price at Myerson. So actually for Myerson, we didn't prove it directly, we proved it from this theorem. But they do not hold for the first price auction. For the first price auction, the result is true, but we had to prove it specifically for the first price auction. And the reason it doesn't hold is because of this boundary layer. You need to assume some uniformity in the derivatives in order to get this theorem. And for the first price auction, we saw that it doesn't work. But we do believe that all asymmetric auctions are order epsilon square over n cube revenue equivalent, but we still don't have this result for any auction. So, okay, I think it's a good time to stop and acknowledge again my collaborators. All the papers are on my homepage, and if there are any questions, I'll be happy to answer.
Thank you very much, Gadi. It was a very interesting talk. And are there any questions, comments? Janusz?
I have one question, but this is a very weird one. So I wasn't sure if I should ask, but I don't know much about auctions at all, I have to admit beforehand, but when you started to talk about the numerical results naively, I was expecting that we would see expressions when something is taken to the power n. If I look at a one-shot game, for example, I want to calculate what is the probability that everybody is playing the first action, then you would get this type of things, right? Something to the power n. And in your calculations, mostly we've seen it was rather n to the power something, like the mistakes were 1 over n to the power 3, right? Order, that's n to the power minus 3. Is there some very specific reason behind it why it's not never something to the power n? It was just my very naive expectation beforehand, but
I'm not sure I understand, but let me try to answer. Maybe I answered the wrong question, but let me try. Indeed, when you have n bidders, then you do have powers of n in the integral. But if you do if you have an integral with a power of n and you do integration by parts, then you get 1 over n from in the expansion of the integral. So indeed, all the expansion for the revenue have f to the power of n or n minus 1 and whatever. And from this, indeed, you pick all these power series in n.
okay, and then in the mistake it disappears somehow. I see. Okay. No, anyhow, thank you. It was.
Yeah, Francoise, do you have a question?
Yeah, well, it's more like a comment or a very vague intuition. I think that was already in Wilson. When you go to many bidders, somehow there are many things that can happen. Maybe auctions are not so appropriate when there are many participants. And so it might be that the two standard auction format give the same revenue just because another mechanism is at play. And that, for instance, the seller can extract basically the full rent because he expects to be, you know, some form of competition or so much competition between the bidders that he will extract the maximum or get close to something competitive. So I'm not sure this is relevant and is a side comment, but I think we have to be very careful when we analyze auctions with many bidders. No?
Yeah, I think many of the assumptions of auction theory are not realistic. Also assuming people are in play according to Nash equilibrium and they know the strategies of the other and they know the distribution. I think of this as pure math, not as a real something that tells us about the auctions. But what I can say...
Yeah, go ahead, please. Sorry.
What I can say is that when we say large auction, it can be n equal 8 or 10. It doesn't have to be 1,000. Because of this 1 over n cube convergence, even if you have 10 bidders, which is still not a very large number, the difference would be in the 3rd digit. So I agree that if you go to thousands of bidders, yeah, surely the model is wrong. But the focus of this, that's why the n cube is very important, because it means you don't have n to be very large in order to rely on these results.
No, the answer is extremely useful. So it's really, it goes much beyond what I had in mind. It's a precise answer. No, my question had nothing to do with realism. I mean, I don't care about it. I'm very interested in consistency. And another comment is that if there is one framework where auction theory has been successful in practice, it's precisely auction. So we should not be shy, you know, whether we are game theorists, mathematicians, economists, whatever we are. I think we shouldn't be shy and careful. I mean, auctions, it seems that they did very well. So that was certainly not a criticism, but your answer was just perfect. I mean, of course, what large means is very relative, and you give a precise answer to this. Thank you very much.
Thank you.
Are there additional questions, comments? Okay, so thank you very much, Gadi.
Thank you.
And we'll meet again in 2 weeks.
Thank you very much. It was very